Ciao a tutti, bentornati a una nuova puntata della serie di intelligenza artificiale di Liberi, Oltre, STEM, e oggi abbiamo un ospite speciale con noi, in particolare Dan Adams di Neuralink, che ci parlerà appunto di Neuralink, e Luca Ducceschi e Fabio Stefanini, che già conoscete diciamo da altre puntate, da altri episodi precedenti che abbiamo fatto nella serie di intelligenza artificiale, condurranno l'intervista, che sarà in inglese chiaramente. Quindi poi comunque avrete la possibilità di attivare, suppongo, la trascrizione automatica dei sottotitoli tramite YouTube, che comunque sono diventati, grazie all'intelligenza artificiale, molto molto precisi, quindi non dovrebbe essere un problema. E perciò niente, senza indugiare oltre, io adesso mi levo e mi metto nel backstage e lascio la parola a Luca e a Fabio per continuare l'intervista con Dan.
Right. Bene, grazie Luca. Dunque anche io passerò immediatamente all'inglese. Dan in realtà un po' si vergogna, capisce un po' di italiano perché ha vissuto in Italia, specialmente a Rovereto, però insomma per motivi di semplicità faremo questa intervista in inglese. So, Dan, hi, welcome,
Hi.
and thank you for your time.
Thank you.
It's great to have you here.
It's a pleasure.
So let me ask you the first question. So who is Dan Adams? Because I don't know, we know you, but I think, it would be better if you could introduce yourself and tell us a bit more about who you are and why you are there.
So I consider myself to be a former scientist. I spent my career pursuing my scientific industry interests in neuroscience, and particularly in the visual system. So for the last 25 years or so, I've been studying binocular vision and stereopsis, how the brain calculates depth by looking at the differences between the image it gets from each eye, and also what can go wrong with that process in kids who grow up with strabismus and amblyopia. And after a substantial amount of time working in the lab, working with non-human primates, recording from the visual cortex and doing anatomical studies, I eventually kind of realized that the part of science that I enjoyed and got the most kind of reward from was actually the craft of science. Not really the science itself, but just the actual doing it, producing things, working with my hands, working in the lab, solving practical problems. And so I kind of decided to make a big change in my career, and moved into an industry where I would be able to do more of that. The problem with science is that the longer you stay in it, the less practical side of it you end up doing. You end up writing more papers, writing grants, supervising students, giving talks. And what I really missed was just using my hands in the lab. So the beautiful thing about an industrial position, and I think specifically the one at Neuralink, is that we're actually building something, we're doing something and making something that works. And what really drives me every day to come to work and enjoy what I'm doing is the idea that I'm not being judged by a paper or an academic or reviewer number 2. The only real measure of success is, does this thing work or not? And you don't need a reviewer or anyone else to tell you that. And so it's great to be in a much more hands-on kind of, I guess, a more engineering position and less science position. So that's sort of my kind of my career path and how I ended up here.
Yeah, and while writing papers, you end up in Rovereto at a certain point, which is why we know each other. I think that it's
exactly. Well, the one part of academic science or academia in general that I miss is teaching, and and that's an entirely separate pleasure, which I miss a lot.
You never know. So yeah, okay. So the reason why we are talking to you is actually because there has been a great deal of news coming from your side of the world, from Neuralink. So what's happening out there?
Well, I don't know if there's been a great deal of news. There's been a great deal of speculation, but essentially we've been working on a medical device that can record signals from the brain, can record signals from individual neurons with electrodes that are microscopic, inserted into the cortex. And the first application of this device is to record from the motor cortex, and the part of the motor cortex that controls hand and arm movements. And so the first application of this is in people who have lost control over their motor system, people with spinal cord injury or amyotrophic lateral sclerosis, where everything is working perfectly well in the brain, but the signals can no longer go down the spinal cord and control the muscles. And so the application is to record those signals at their source in the motor cortex and use them to control something else that is not the muscles, like a computer cursor on a screen. So people who until since their injury have only been able to control a computer with something like a stick that they hold in their mouth to prod at a touch screen, can now control the cursor and click just by thinking about moving their hand. So as they think, the cursor moves, and they basically gain control of a computer. And obviously, to do this, to make this a real product, we have to have it approved that it's safe to install in humans, and for that we've started a clinical trial under the supervision of the FDA. So if everything goes well, in a few years' time, we'll move into the next stage, which is then to prove that not only is this device safe, but it's also effective, and then eventually it'll become a device that can be given to people just to help them in everyday life. And we're not the first people to develop this technology by any means.
Which is my next question, actually.
Yeah. So people have been working on this as a principle for controlling a computer or controlling a machine for more than 20 years, and people have been very successful in installing this in people mostly in laboratory and research settings. So this means taking a subject and then basically installing the device, and then that person basically becomes a professional experimental subject for the foreseeable future. Our approach is different. We're not developing the science, we're not doing research, we're developing the technology to make this device into something that can be operated without a bank of computer racks and without a team of postdocs, and something that can be done by a person, outside, sitting by their swimming pool, operating a computer without just them and a laptop, or them and a cell phone. No big banks of equipment, no wires coming out of the head, everything wireless, and everything just as a normal consumer electronics system should be. And so we're not really, as I said, we're not doing science. We're a technology company making a device that is proven to work in scientific labs into something that can help thousands of people instead of just a few people in science labs.
All right. So Fabio, I have plenty of questions, but of course, please feel free to interrupt.
Yeah, I wanted to interject on this aspect of the technology versus the scientific environment. There are definitely different several aspects of the device that need like optimization to become a product that can be that can be sold to people rather than used in laboratory settings, including the surgeries themselves, and then also the use, as you were probably referring to, by being able to use it in everyday life, and being able to have a system that tells you whether it's working or not working, and what to do when it's not working, like the phone that we have in our hands every day. Whereas in university, these things happen, the supervision of a scientist, of a postdoc, and so on. So regarding the surgeries themselves, is it something that is that an aspect that is also being researched on in terms of like making it available to most people, such that instead of going to a university that is doing some experimental project, you could actually go to facilities that implant these chips on a massive scale?
Yes, exactly. That is the aim. That we will eventually, this will become a very low risk, a very fast and a very convenient surgery that people will go to a Neuralink clinic where there will be a number of operating rooms, each with, one of the things I haven't mentioned is that to put these fine electrodes in the brain, we have to actually use a computer. They're too fine to be handled by any surgeon. So they have to be installed with a robot. And so we will have Neuralink clinics, just like LASIK eye surgery clinics, where people turn up, go in, have the device installed, and leave the same day. That's the intention. That's the ambition. And by lowering the amount of investment that it takes to install the device and raising the volume of people that can have this accessible, that's the only real way to make this become a technology that can be available to the masses.
So how much do you think, like as a quick follow-up, so how much do you think they innovate? Yeah, how much innovation do you think there is in this part of the project rather than in the optimization of the actual, decoding system that sits on your brain? I guess, I mean, to me as a decoding scientist, I can probably see how the decoding part can be made like super efficient, super optimal. I think that's not a problem, maybe just because I know the details of it. To me, the surgery itself, it's super innovative because none of that has been done before, like having a robot that can do that with that level of precision. To me, it looks like that's the real innovation.
You're absolutely
I don't know if you share
that
this.
That is 99% of the difficult part. Even developing of the technology to a certain extent, and the decoding of the algorithm and making it work to a certain extent, even that is kind of the easy part. The hard part is making this into a device that can be available and will be a successful product to help thousands of people. A good analogy would be, anyone can build a car in their garage. Many people do. They restore cars or rebuild them or make them from scratch. But the difference between doing that and producing a successful car factory or successful car company is 99.9% of the difficult part. So exactly what we're working on is a way to take these devices and this technology that we know works, and actually allowing it to be helpful to the people who need it. Yeah, and you're right. The difficult parts are scaling things, making things simple enough that they can be produced reliably and at scale, and just making this into a non-prototype device. Yeah.
So just quickly.
So that involves everything from the design of the device itself to the procedure, the surgery, all the instruments that are used in the surgery, or and every part of it, from the patient coming into the OR to having a functional device, has to be optimized and simplified and made to work at scale. Yeah.
Can I ask you something about this aspect, Adams? So, Dan, sorry.
Sure.
Why are you the first ones? Why do you think that? I mean, it doesn't look like there's a huge competition out there. The technology is old. The idea in itself, it's old. But Neuralink, it's somewhat of an exception. So why do you think it is?
I think because it's just not a very. There's a long runway before you can make this into a profitable industry. Trying to make it into something that can work at volume. I mean, everyone else has looked at this as a sort of science project to develop the technology, usually academia, and no one's actually said, okay, we've learned enough about it scientifically. It can work now, and so I think we're just by chance are the first people who've actually thought about this in terms of an industry instead of a science project.
Yeah, you have to admit that it's still surprising in a place like the US, where basically everyone is hunting some sort of new business opportunity. This is like an incredible industry sector, and again, it looks like maybe there is like a different the background that I don't see. Not being in the US, it's what I miss essentially. But it looks like Neuralink is an exception, which is still unbelievable to me. But so, okay.
I mean, there are other companies looking at this, and it's I think it's unusual in the sense that, as I was saying, there's a long runway to becoming profitable, and so we're in a really unique position where we are obviously, we want to become a profitable company, but we have a long time to do that, and we have like secure funding until we can really ramp up the volume. And I think this is probably just more true of some industries than others. Yeah.
Also,
can I?
Yeah, go on. Absolutely. Go for it.
I wanted to follow up on I wanted, like, for the sake of scientific arguing, I wanted to ask about, like, you mentioned a few times, this is sort of a working technology. Like we definitely have like scientific results on implanting electrodes or even imaging devices in various species, even in humans, in epileptic patients that need surgery for detecting the locus of epileptic seizure, but even for restoring motor abilities. Right. And so bringing it to scale, definitely that's the challenge. But one thing, as far as I know, one thing that is also kind of peculiar of these endeavors is that in such a scientific environment, you can tailor the system, including decoding the algorithms, the specific tasks, and the placement and all these kind of issues to the specifics of the patient themselves. Mm-hmm. In a sort of a more mass available system, in that framework, how do you envision supporting whatever types of functions that people may want to support, whatever type of, the different brains? There are so many things that we don't know about the brain. Like, I understand like how the technological achievement of being able to implant a device on a massive scale, that has a clear target to me. And I think whether it works or not, there's going to be so much technology coming out of that endeavor that it's, the whole of humanity is going to be benefiting from that. I don't have a clear idea of exactly like how the implant itself and the ability to decode the brain activity of the implant itself can serve the purpose of the large masses. So, okay, so could you help me there?
Exactly. So it really depends on the exact application that we're following. The first application, as you know, is decoding from motor cortex. So for that, every individual will have an fMRI study that will identify the region of their brain that would formerly control their limbs. And we use those fMRI data to target the electrodes very precisely into that region of the cortex. And that's going to be something that will be part of the standard procedure for implanting people for this particular application. Another application will be for people with who've lost limbs, amputees. And so we can also control, instead of controlling a cursor on the screen, we can also control a robotic prosthetic arm. And not only can you control it through the wireless connection from the Neuralink, but you'll also be able to feel sensation from it. So the prosthetic hand would have sensors in the fingertips that then can produce stimulation of the somatosensory cortex. So the person will be able to actually not only move their hand, but actually get sensory feedback from it. And again, these regions of the brain are very well defined. We have a whole long and rich history of scientific research on these areas. And so we're not putting electrodes anywhere in the brain where we don't know what we're going to find. Another application will be for a vision prosthetic. This is something that I've been particularly interested in. So for someone who's completely blind, you can stimulate their visual cortex using the output from a camera. And again, the mapping of the visual world onto the visual cortex in humans is incredibly well understood and very well and characteristically organized. So we know where to put electrodes in the brain to produce visual perception in their visual fields. So these kinds of early applications are just on the working on the back of a huge amount of scientific research. Beyond that, as you said, you mentioned epilepsy is another application. So again, it's known that people with some forms of epilepsy have a focal seizure point in their brain that can be sometimes identified just with an anatomical MRI scan. So we can put electrodes into that region, and the device could start out by being an early warning system, telling them, maybe sending a signal to their smartphone or their watch or something saying, you better sit down, you're about to have a seizure. But then we can also stimulate those regions and find ways to curtail the early activity that might result in a seizure. So, there are lots of applications that are going to be extremely beneficial to people, but about which we don't need to learn anything new about the brain. We have enough knowledge to simply apply our technology to it without having to, unearth any of the sort of mysteries about the brain.
So, in a way, Neuralink is the device, whatever the commercial name will it get. I don't know if you have something in mind already, but it's going to be some sort of gateway into the brain. So something that might help to get something as output from the brain. So moving a limb or something as input, seeing something or feeling something that you couldn't feel before. And also it might help stimulate the brain in different ways to do other things that we still cannot probably foresee because, it's a long shot between here and then. But also, do you think that it will be capable of being used as a scientific device? Can we observe the brain in a way that we were not able to observe before or not? Because it feels like it's a huge advancement. It's like it's going to be better than fMRI in a way, or the MEG in many ways. I don't know if I am.
Yeah, I think there's certainly huge potential for it to be used in science. We are in touch with a number of scientists who would love us to put the device into animals so that they can record signals, for example, from a monkey while it's just running around in its cage, swinging around on trees and behaving normally. And it's never been possible to stream neural activity from in that kind of environment without having cables, without having a great deal of technical difficulties. So it's certainly will be an extremely powerful scientific tool. And as a scientist myself, I also feel like that we have an obligation to put this into the hands of scientists so that they use it as an instrument, just like any other scientific instrument. It's certainly hopefully, and this is what other companies, for example, BlackRock, the developers of the Utah array, have done. So they developed a device that is also FDA approved for use in humans and has produced a great many humans who have a brain-computer interface, who can interact with a computer, paralyzed people, and they've even been able to stimulate to produce sensations. Basically done everything that we're trying to do already. But they also sell their device to scientific labs who use it for research. So there are some difficulties surrounding our specific device for this. For example, as I said, we need this giant robot to install the device. So that just makes it a little bit more difficult to make it available. But this is certainly one of the objectives of the company. Once we have this working in humans, to say, listen, let's as well as implanting humans in our clinics, we can perhaps also have academic centers where people will be able to bring animals or to have them implanted. So, we're definitely enthusiastic about people using the device for scientific purposes, but our prime motivation is not science. Our prime motivation is to generate a medical device.
Yeah. Bobby, do you have any other question? I mean,
no, we definitely have plenty. Yeah, I was going to comment on what you just said, like comparisons with available systems. Like what maybe at least part of our audience don't know is about these other systems that already today allow us to record from remote parts of the brains in different species, and that's how most of the more modern neuroscience is moving forward in understanding brain functions. There's a lot to discover, but really being able to replace students and postdocs in doing the surgeries to me sounds massive. Like being able to really use it as a go to a clinic and get an implant. I mean, even we know how to use it, and we take it like we believe to some extent we can do that, but having it as an available tool to a huge number of clinics around the world, if that becomes a reality, I can really see huge potential.
Yeah. I do have a comment on which is also a follow up on that. So besides, like, it's not going to be easy. We know that it's going to be it's going to be a long journey between now and the moment where we will have clinics all around the world that can perform this kind of surgery. This is just one of the curiosities I have. Like, do you see any sort of like major bottleneck between now and then? Is it going to be the availability of the robots, the technology behind the robots, the ability of the FDA approval, long, I don't know, procedure? Is there going to be what are the major challenges from a technical perspective?
I think most of the bottlenecks will be regulatory.
Yeah.
At the moment, we have a device that works and is working in a great many animals and has been in animals for a long period of time. But obviously, there are very important rules and tests and regulations that need to be passed before it can be available as a standard therapy. I think the technology moves faster than the regulatory bodies. I think that's always been the case in pharmaceutical research and medical device research. I think that's the major bottleneck.
Right.
Can I ask one thing on that maybe is about, like, how long do you, after the implant, how long do you envision people being able to keep the implant? How long is it going to work? Whether they need replacements? What's the research that has to be done there in order to be able to carry a brain implant for, I don't know, maybe your entire life, which is, I'm not sure how far we are actually in academic settings with that.
Well, there are a number of limiting factors on lifetime. One of the major limiting factors has been that electrodes inserted into the brain, over time, there's a sort of foreign body reaction, and scar tissue and things like cells called glia produce scars around those electrode tips. And over time, the electrical performance goes down. The sensitivity to be able to record signals from the brain is decreased. And so that's until now, that's been the major limiting factor, certainly in terms of the Utah array, for example, has a life-limiting step that is basically that biological process. One of the things that we've looked at very carefully and I think is very important is to increase the lifespan of these devices. Our electrodes are very thin and very flexible. So as the brain moves inside the head, the brain is a very soft material, and as you shake your head, waves of movement move through it, and our electrodes actually flex and move with the brain. So this actually reduces the amount of scar tissue that can build up around them, as opposed to the UTRA, which are rigid, like little rigid spikes into the surface. So that, for us at least, is no longer a limiting factor in terms of functional lifetime. At the moment, our device has a lithium-ion battery, and as we all know, lithium-ion batteries have a finite lifespan. At the moment, that's probably the limiting factor on lifetime for us, but batteries are one of the highest technological areas for research and development, and as battery life increases, then the life of so what I'm trying to say is that, like, every aspect of the implant will have a finite life period, and the whole implant will be limited by the one with the shortest lifetime. So as we solve one problem, then we'll get to the next one. So as we make the threads longer lasting, then we'll have to make the battery longer lasting. As the battery gets longer lasting, maybe the materials, some other property of the material, the shell of the case, for example, or some other issue will come along. So that'll be a constant development stream in improving duration. Yeah.
Okay, I don't know if I'm asking you questions you have no answer to because it's too far-fetched, but I'm a linguist, as you know, and so my interest is also in the problematic part of the language in the brain. So do you see any application that might come out of this device and this technology that can help people that have had a stroke and have had some sort of aphasia of sorts, like people that cannot? Because in that case, there is damage, and we haven't talked about damage in the brain. We have talked about damage around the brain. You see any possible application in that sector?
So that is obviously, if the part of the brain, the part of the system that you need to get information from itself is damaged, then you have an extra challenge. With quadriplegia, for example, all the motor cortex of the entire brain is entirely intact. The only problem is in the spinal cord. But as you say, with problems like stroke, where there's the actual brain tissue that becomes compromised, then the bets are off, and it may be more difficult to actually produce a useful device. I think some of the problems that with language that have been addressed so far are people, for example, with ALS, who although their cortical circuitry for speaking is intact, the problem is with production itself, with the motor part of it. And so the people have, especially the work of Eddie Chang, for example, at UCSF, have made incredible progress with producing speech in people who are incapable of speech. But as you say, if it's the brain that's actually damaged, then you have a more fundamental problem. It may be possible to record from alternative parts of the brain that can carry sufficient information to fulfill whatever task it is, that whatever system it is that you're trying to bypass or trying to help. But there is a fundamental limiting factor there, that if this is a device to record from the brain, so if there's brain injury, then you have an extra challenge. Yeah.
It's fascinating, the perspective that you might be able to acquire enough data from the many devices implanted in people in the future, and then build some sort of projection or prediction, so that you could collect in principle data from around the damaged area, and then thanks to a model of sorts, a language model, an AI system, you might be able to some sort of predict what the person might want to say based on a fewer features. I don't know. Yep. This is very far-fetched again, but we are talking about something that is very close to sci-fi. So
absolutely, I mean that's certainly an avenue. Yeah, and the other application, or the other thing that you may be able to do as a therapeutic approach would be to stimulate. So as well as recording, our device can also stimulate, and it may be possible to augment function by stimulating various parts of the brain. This is something that's done in Parkinson's, for example. They can stimulate parts of the basal ganglia to overcome losses in functionality of other pathways. So this is also an approach that can be taken even in a neural system that's damaged or compromised.
How many years down the line do you think we should? Sorry, Fabio.
No, go ahead. That's a good question as well.
How many years down the line do you think we can expect to see significant application? Like we can expect to to be able to say something like one of my friends had an implant or something like 10 years, 20 years, 5 years.
We're very ambitious and very optimistic, and we're trying to move as fast as possible. We have an ambition to have, I think, 22,000 people with implants by 2030.
Wow.
So as soon as we have permission from the FDA, and as soon as, not just permission from them, but as soon as we've satisfied ourselves that this is a safe procedure, then we'll be expanding exponentially and implanting hundreds or even thousands of people a month. Yeah.
Fabio.
Yeah, I was going to ask, now 2 questions. One was about more technical one. You mentioned basal ganglia, so I was wondering whether the surgery robot can only access the surface of the brain, the cortex, where some of our motor function or decision functions and language functions are supported, or whether you could go down to hippocampus, parts of the brain, or amygdala, parts of the brain that are more involved with our most basic desire needs and cognitive functions. The other question is going to be more about the machine learning attached to it, but
sure.
This is also...
So the current generation of the robots can insert down to 50 millimeters, 5 centimeters. There are additional risks and challenges that are faced with going deeper than just the surface. So one of the major things we've concentrated on is avoiding blood vessels. So when you're inserting into the surface of the cortex, of course, you can see all that beautiful matrix of blood vessels on the surface. But if your electrode passes underneath the surface and goes into sulci that are buried deeper in the brain, there's always a possibility that you may cause a bleed inside a sulci where you can't see it. So in order to be able to do that, and this is something that we will need to be able to do, for example, in a visual prosthesis, because much of the visual cortex is buried in a sulcus at the back of the brain called the calcarine sulcus. So to stimulate beyond about just the central couple of degrees of visual field, we'll actually have to insert electrodes quite deeply. And so this will require a full study of safety and a separate endeavor. So, and then beyond that, of course, we can stimulate the basal ganglia and the kinds of regions that you mentioned, the hippocampus. Everything that we do is driven by an application. So the application for stimulating basal ganglia might be movement disorders, for example. But on the other hand, we also want to be able to do something that is not possible already. The application has to suit the technology. So, for example, it might not be worth putting thousands of electrodes into basal ganglia when we already know that people can do DBS and solve problems like Parkinson's disease with only a few. We have to basically find the application that suits our particular niche. This is something that we looked at in spinal cord stimulation. So one of the applications was to produce, to actually stimulate the motor neurons in someone who's paralyzed so that they'd be able to move their own hand, even though they had a spinal cord injury. And so to get fine control, for example, we would want a great many electrodes in the upper motor neurons to get fine control of the hand. Other people have looked at this with many fewer electrodes, stimulating spinal neurons that control the legs, and have had huge successes in restoring walking movements. every application, we have to find the right niche for our specific technology.
I was going to ask, if I can, about Luca mentioned the data. So obviously, this machinery will require to record the data, do something with it, and then either stimulate parts of the brain or produce something with a digital device as a true brain-machine interface, controlling a cursor, controlling a robotic arm, or things like that. So do you think, obviously the vision will be to have these algorithms be, very local, so that everything happens on the chips themselves to be able to perform those activities. But I assume or imagine for the first, for the first trials and for the first research, you will need to collect this data, and how much do you envision that that Neuralink will need to collect the data of, like, even the 20,000 patients that it will reach in order to be able to support those activities efficiently?
I don't think we will need to. This is basically an automated process. Even at the moment, it's an automated process. We've written software for calibration of the device, and everything works entirely autonomously. So the subject sits in front of the computer, goes through the calibration sequence, and from that point, they can control the cursor on the screen. It's a process that takes just a few minutes and doesn't require any outside engineering whatsoever. A lot of processing of the actual neural signals is done on the device itself, and the main reason for this is just because there's a quite a narrow bandwidth of communication from the device to a computer. We actually use just Bluetooth, normal low energy Bluetooth, and so in order to get information, we can't send out the raw traces of every single neuron. What we have to do is basically detect what are known as the spikes, neural action potentials in the signal, count them, put them into bins, and then stream that sequence of bins out of the device over Bluetooth. But all of the algorithm and the analysis of the signal is then done for example, on an app on the phone, or in a program on a laptop if you connect to a laptop. And all those analysis systems are running entirely without any kind of human input whatsoever.
Right. So that's also why the capacity of the battery is going to be much relevant, because you need a lot of computational power. So that's going to drain the battery.
Yeah.
Because computation happens at the brain level, in the device, right? Not part of the computation happens there, so you're going to need some power there.
Yep. Okay. Actually, the biggest power hog on the battery is the radio, is the Bluetooth.
Yeah. Makes sense.
The actual amplification and the spike detection, we obviously have custom silicon that runs all those processes. The spikes are actually detected in silico in hardware on the chips themselves, with incredibly short latencies. All of that is fairly energy efficient. It's when you have to power a radio transmitter that you begin to eat through battery.
You need power then. Yeah. All right. Yeah. So I have a couple of questions that are a little bit more pop than science, but I'll go on, and if we have extra scientific questions, I think we can go back to them. But there's let's say, let's start with this. And this is a question probably many people ask you, but you have been a teacher, so you know how relevant this is. But now you are a student and you want to continue, you want to do your PhD, you want to think about your career, and now you have something and if you're a cognitive student, you have Neuralink now. So besides doing the obvious internship, what would you advise a modern cognitive student who has some sort of ambition to work in the industry sector to do? How to get to a place like Neuralink in a very comfortable way? Which kind of skill sets? What's your advice?
So, working in industry is, as I've said many times, it's not science. And so you need to have more than ideas. We're not looking for people with ideas. Doesn't mean that you can't have ideas, but it means that that alone is not a good qualification. You need to actually be able to do things and get things done. And so advice to someone looking for a position in a company like Neuralink would be make things work and do things, and prove that you will literally be able to, do things with your hands, do soldering, do electronics, make things in a machine shop, understand mechanisms, understand engineering principles, understand electronics and computer science, and prove that by solving problems. And the wonderful thing about a scientific career is it puts you in a beautiful playground of instruments and tools and technology where you can enjoy building things, making things work, and solving practical problems, which in themselves are not science, but they are the necessary parts that you have to do science. And the more that you can specialize and go deep on a particular field or a particular problem, and come up with real solutions to it, then the more valuable you will be in applying that problem or addressing that particular challenge in a company. In terms of academia, a PhD is useful because it is basically like a driver's license for research. I think a lot of people go into a PhD thinking that it will in and of itself produce some kind of, people think they're going to get a Nobel Prize for their PhD thesis, but really what they discover after doing a PhD is that absolutely everyone around them already has a PhD, and so it's like a welcome to the club moment. And the PhD is exactly a driver's license to do science. And if you're not going to do science, then it has limited value, except for the actual practical things and the practical problems that you had to solve to do your experimental PhD. So my advice to anyone would be get into the lab and start building things, start making things. Yeah.
Right. I mean, Fabio probably has to go, I suppose, but
yes, I was going to. Unfortunately, I have another meeting here in New York. It's still work time, and I'm not as important as Dan. I still have to go and join meetings. So thanks. This was really a pleasure to talk to you, and sorry that I have to cut it short.
No
Thanks
problem.
a lot.
We are probably going to wrap it up soon. So, but thank you, Fabio, very much.
Thank
See
you.
Soon. So, okay, then let me ask you a final question, and then we can improvise after that. So, but you mentioned the bottleneck being the regulatory body of laws and everything, but it still feels like that something like Neuralink could have happened in the U.S. and as a matter of fact, it did, but it would have been somewhat more difficult for it to happen in Europe. But this is my perspective. European regulations are too strict for an innovative company like Neuralink to rise, or not? What's your take?
I'm not an expert on the different regulatory bodies, but my understanding is that the FDA are very stringent, rightly so, and very strict. And once that you have FDA approval, then getting approval for the European and the Asian and the Australian equivalents is streamlined somewhat. So I don't think differences in regulations have been the reason for the sort of the lack of a Neuralink 10 years ago, for example. I think the real reason is that this was always going to be a very expensive and long-term proposition to do it from beginning to end. I mean, the wonderful thing about Neuralink is that we're we have almost perfect vertical alignment. So we build our device, we make our electrodes, we do our own, we build the robot, we do every part of this, and which has huge advantages that we're not relying on anyone else. We can have very fast iteration cycles because we're in control of all the technology, but it makes it extremely expensive. And without an enormous amount of investment, that not every venture capital company is going to be patient enough to wait for not only the development of the device, but the entire sequence of FDA trials, and before you end up with a device that, even when you have revenue, is also going to take a long time before that revenue can become profitable. So I think it's unfortunately, I think it's a financial argument that this is not a highly profitable business, and so there's just no appetite for the long-term kind of investment that is required to get something like this to a position where it becomes a normal medical treatment.
Makes perfect sense to me. I tend to agree with you, I would say. Yeah.
Mm.
Well, it seems to be like it's you and me at this point, and I really have no further questions, unless unless you have extra comments you want to donate. I don't know if Luca has extra questions, or if you just...
No, actually, I don't. I mean, it's been a very nice chat that I was hearing in the background. So thank you a lot, Dan, because it was really, really interesting to get to know how it works and what it could do in the future, Neuralink. Yeah. So with this, then yes, if you have any further remarks, Dan, please go ahead.
Not really. I think it's a real pleasure to talk to people who understand what we're doing somewhat. I think there are a lot of misconceptions about Neuralink, and
thank you a lot.
I look forward to sharing more information about what we're doing.
Yeah, we look forward to it. Yeah.
Yes, absolutely. So we're going to be here for you if you want.
Cool.
All right.
Thank you. So thanks, and we'll see you soon if you will want to come for another talk. You will be most welcome. Yeah.
Okay, great.
Buon lavoro allora.
Grazie. Ciao.
Then. Ciao.
E ok, grazie a tutti, grazie Luca per aver condotto l'intervista, grazie anche a Fabio che ci ha lasciato prima, purtroppo per altri impegni. E niente, io quindi a questo punto vi saluto. Comunque, come al solito, vi consiglio di mettere like, fare girare il video e iscrivervi ai canali di Liberi Oltre, iscrivervi all'associazione di Liberi Oltre, e ci vediamo alla prossima puntata della serie di intelligenza artificiale. A presto, grazie a tutti.
Luca, grazie a tutti e a presto, buona serata.